Welcome back. As you see, we got kind of a chunky statement to read through, but I think what the point is that we got to get used to dealing with the ways to draw out events in space-time using space-time diagrams. So with that, let's get started. All right. So the statement reads: inertial system S bar moves in the x direction at speed 3/5 c relative to system S. A. On graph paper, set up a Cartesian coordinate system with axes CT and X. Carefully draw lines representing x bar equal -3, -2, -1, 0, 1, 2, and 3. Also draw in the lines corresponding to CT bar equal the same values and label your lines clearly. All right, first and foremost, got to set up everything we need. Part B, in S bar, a free particle is observed to travel from point x bar equal -2 at time CT bar equal -3 to a point x bar 2 at CT bar equal +3. All right. Indicate the displacement on your graph, and from the slope of this line, determine the particle's speed in S. Okay, be careful. You need to understand how these graphs are constructed. Go back to the Minkowski diagrams and the spacetime diagrams. C. Use the velocity rule to determine the velocity in S algebraically and check that your answer is consistent with the graphical results. Okay? Well, that being said, what we need to understand here is that the inverse of the slope gives us the velocity in a diagram. That was one of the things that was weird about these constructions. So I'll show you the graphs in a second, but let's just take a note here of what B and C are asking so we can check that when we do graph it, since it's going to be all at once. The slope is going to be equal to C over V, which is what we read off. So here we'll get 9.25 over 8.75. Solve that for V, we see that we get 35 over 37C. No big deal. And then for V prime for C, we get the same value here. Using the velocity addition rule. So our graphical results and analytic results at least match if we read off everything from the graph right. But let's go see what this vaunted graph looks like. All right. So this being said, let's take careful note here that if we have CT here in the vertical and X here, which is normally what we had reversed in classical mechanics, where we had position in the vertical, time on the horizontal. Now we're flipping it. The reason why is because now we need to see how the transformations work, and the transformations happen on these slanted lines. Okay, so you see we have the X bars up here, and you notice that they have to run at a tilt here because we run at a, in the transformation, if you go back to Lorentz transformation, X bar was composed of not only the X coordinate, but also a T coordinate. So you have X plus VT. That being said, X plus VT takes a linear line slope. Similarly, with the CT transformation, we had CT being a composition of the T and a V over C squared situation. And so that being said, that's still in the form of a linear line. That being said, where we go for matching these lines, well, remember we were interested in what happened at something like x equal -2 and CT equal -3 or 3, one of the two. It's really hard to see on this graph, so we'll just be careful. But here's that point. And then we move to another event where we have x equal 2 and CT equal +3. -3, run down. So be very careful how we deal with these. But that being said, what we're interested in is if our horizontal in X is 8.75 and our vertical in CT is equal to 9.25, then the inverse of that gives us the velocity. So we're actually very cool to draw in the diagram lines if we know what the relativistic or the speed difference between the two is. And then we can just do a slope formula, which is really easy to do graphically. Now be careful because there is a special case of this where world lines need to add up and the light cone, that kind of thing will come in. So we can have an arbitrary amount, but what is actually physically possible for our understanding now may not be available, but we can still theoretically compose a thought about it. these get annoying really fast. As you can see, it's kind of chunky, but it's still a good task to use. And again, physics involves more than just a calculation. We need to see it drawn out. Diagrams are useful for this, and that's where this value comes in. That being said, we'll maybe see a few more like this, but I think having the concept that X bar is composed of X and CT, and T bar is also composed of T and X. I think we can see how that works together now using slopes. With that being said, I'll see you at the next one.